Hello everybody, welcome back to Math 251. Our mathematician of the day today is Albert Cox. He was the first African American to earn a PhD in mathematics in 1925 from Cornell University, and he became a professor at Howard University, which is pretty amazing. And did you know that ancient Babylonians knew the approximate value of pi, which is pretty incredible considering we are still working on figuring out the exact value of pi. The exact value doesn't exist, but it's amazing that the ancient Babylonians knew this approximation. So today we will be discussing the idea of infinite limits. So first we have our definition of what this means. So suppose f is defined for all x near the point A. If f of x grows arbitrarily large, this grows arbitrarily large, this means goes to infinity. For all x sufficiently close but not equal to the point A, then we write the following. The limit as x approaches A of f of x is equal to infinity. We read this as the limit of f of x as x approaches A is infinity. If instead of getting really big in the positive direction, I'm getting really large in the negative direction, we write the limit as x goes to A of f of x equals negative infinity. So this is what it means for a function to have an infinite limit. In both cases, the limit does not exist. Sometimes we will ask you to specify if it's positive or negative infinity, but our limit does not exist in either of these cases. So hey, congrats, you finally understand that Mean Girl reference. Way to go. Our first example, we want to analyze these two functions and their limits using the graph of the function. We're going to use desmos.com. So let me pull up this. This is desmos.com, a wonderful website. So our function is x over x squared minus 1 squared. So my first one is I want to look at the limit as x goes to 1. So if I look at x equals 1, that's right here. And as we can see on both sides, my y value is getting super big in the positive direction. So because this is happening, I write the following. I write the limit as x goes to 1 of x over x squared minus 1 squared is equal to infinity. If I look at the point negative 1, that's here, then we can see that from either side of negative 1, in the positive and the negative direction of negative 1, our function is getting super large in the negative direction. So we write the following. The limit as x approaches negative 1 of x over x squared minus 1 squared is equal to infinity. So this is kind of what it looks like for a function to have an infinite limit. Notice in both of these cases that, that my function is approaching positive and negative infinity from both the left and the right of this function. So this kind of leads into what we call one-sided infinite limits. We're already familiar with the notion of one-sided limits, and they still apply here. So suppose f is defined for all x near the point A with x greater than A. If f of x becomes arbitrarily large for all x sufficiently close to the point A with x greater than A, we write the limit as x approaches A from the right of f of x equals infinity. We could also approach negative infinity, and we could also approach A from the left instead. So we have three other limits that are really close to this one. So the limits x approaches A from the right of f of x equals negative infinity. The limit as x approaches A from the left of f of x equals positive infinity. And the limit as x approaches A from the left of f of x equals negative infinity are defined similarly to what we defined above. So let's draw some pictures of these. What do these look like? I'm going to call this first one 1. I'm going to call this one 2, this one 3, and this one 4. So let's draw some pictures to see what these look like on a graph. So on 1, I have the limit as x goes to a from the right of f of x is equal to infinity. So I'm going to call this x equals a. And what this looks like is as I approach a from the right, my graph gets super big. So we're focusing on this portion right here. The second one is as, oh sorry. Oh gosh, okay. Oh, erase this one too. Sorry. Just trying to make this a little bit smaller. Okay, the second one is as x approaches a from the right again. So here's x equals a. We're approaching it from the right, but now we're going towards negative infinity. So we're going to go in the negative direction. Next, we have as x approaches a from the left equals positive infinity. So now I'm approaching from this side, the left, and I go to positive infinity. And our last one is as x approaches a from the right, we go to negative infinity. So as I approach a from the left, I'm going towards negative infinity. So this is what it means for a function to have a one-sided infinite limit. This leads to the notion of a vertical asymptote. You have probably seen vertical asymptotes in classes like Math 112 and Math 111, and they come up again here in calculus. So there are a couple ways to define what this means. I'm first going to say if we have something like the limit as x approaches a of 1 over x minus a. If I have this, or if I have the limit as x approaches positive, if a approaches a from the left or the right. So if x approaches a from the left or the right, f of x is equal to positive or negative infinity. In either one of these cases, we call the line x equals a the vertical asymptote of f of x. Most often in this class, we'll see this one. So basically, if I were to plug in x equals a into this function, I would get 1 over 0, which will always lead to our graph either going to positive or negative infinity, since we can't divide by 0. So these two definitions they work with each other, because if I approach a in this kind of function, I go to positive or negative infinity. All right, next we want to use the graph of this function to analyze the following limits. So let's pull up Desmos and graph this function. We have x plus 3, x plus 3 on top, over x plus 1 squared times x plus 1 squared. Nope. Times x minus 2. Okay, so here's what our function looks like. Our first problem is to see what happens at the point x equals negative 1. So we see here's x equals negative 1 right here, and on the left side and on the right side of negative 1, our function is getting super big in the negative direction. So I write this is equal to negative infinity. I'd like for you to pause this video and try parts B and C on your own. Here is what the graph looks like. So go ahead and give those two parts a try. All right, hopefully you've tried B and C. So if I look at the point x equals 2 from the left, I am on this side of x equals 2, and I can see that my y values are getting really big in the negative direction. So the limit as x goes to 2 from the left is equal to negative infinity. And as x goes to 2 from the right, I can see that this is positive infinity because my y values are getting really large in the positive direction. So this is equal to positive infinity. So hopefully that makes sense. Sometimes though we won't have graphs or we won't have access to a website like Desmos, so we have to use other methods to solve for these limits. That's what we're going to do in the next example. We want to solve for these infinite limits using logic and arithmetic. So we first have the limit as x goes to 3 from the right of 2 minus 5x over x minus 3. So I don't have a graph and I don't really know what this graph looks like. So I'm going to have to use another strategy instead. So if I'm approaching 3, first of all, if I plug in 3 into my graph, I'm going to have 0 in the denominator, so I can't just plug in 3. So if I plug in x equals 3, I get 0 in the denominator, which is no good. So I can't do that. Instead, I have to use something else. So if I approach 3 from the right, that means that my x values are slightly greater than 3. If you think about approaching x from the right, 3 from the right, excuse me, we have values like 3.1, 3.01, 3.001. We're getting super close to 3, except we are slightly greater than 3. So as x approaches 3 from the right, my x values are slightly greater than 3. Okay, so if I plug in a number slightly greater than 3 into this expression, I get 2 minus 5x over x minus 3. So 2 minus 5x, I can plug in 3 directly into that one, right? So if I were to plug in 3 there, I'd get 2 minus 15, which is a negative number. It doesn't matter what number it is, as long as I know the sign. So here on the top I have a negative number. And then if I'm slightly greater than 3 and I subtract 3 from it, we are going to get a really small number that is positive, right? If I take 3.001 and I subtract 3 from it, I'm going to get positive 0.001. So this will be a positive number. And a negative number divided by a positive number is negative. And because of this definition of a vertical asymptote right here, I know that I have infinity as my limit, because this x equals 3 is a vertical asymptote. So I get negative infinity. If I look at this problem from the left, so as x approaches 3 from the left, my x values are slightly less than 3. So again, I have 2 minus 5x over x minus 3. I get a negative number on top if I plug in 3. And on the bottom, if I have something slightly less than negative 3, and I subtract 3, slightly less than positive 3, and I subtract 3, then I will get a negative number. So if I have 2.99, for example, and I subtract 3, it's going to be a negative number. And a negative number over a negative number is positive. And again, since this is a vertical asymptote, I go off to infinity. So this is another way to try these infinite limit problems if we don't have access to a graph. Let's do another one similar to this. This time we're going to have to factor. And I know how much we all love factoring. Last term when I taught Math 251, I threatened to make my students a class t-shirt that said, "I love factoring." Luckily, they brushed up on their skills enough so that I did not have to make a class t-shirt for us. I do recommend, if you're not super comfy with factoring, to look at a few examples online to brush up on those skills, because we will factor a little bit in this class. So I want to factor this limit, this function first, and then use the logic that we used in example number 3 to find this limit. So if I look at this function, I have negative x cubed plus 5x squared minus 6x on top over negative x cubed minus 4x squared on the bottom. And I can't factor right away, but I can factor something out of the top and factor something out of the bottom. Well, what can I factor out of the top? Out of every term, I can factor out a negative x. So I'm going to factor out negative x from the top. When I do that, I end up with x squared minus 5x plus 6. On the bottom, I can factor out a negative x squared, and I will be left with x minus 4. And now I can factor the top, negative x. This factors to x minus 3 times x minus 2. The bottom stays negative x squared, x minus 4. How did I factor the top? Well, I knew that I needed two numbers that added to negative 5 and multiplied to positive 6. And those two numbers are negative 3 and negative 2. So I want to find the limit as x approaches 4 from the left of negative x over x minus 3 times x minus 2 over negative x squared, x minus 4. I can cancel out this negative and one of the x's on the top of the bottom. So this becomes the limit as x approaches 4 from the left of x minus 3, x minus 2, x minus 2 over x minus 4. And again, since I would get 0 on the bottom if I plugged in 4 directly into this, I'm going to have to use the logic in example number 3. So if I'm approaching 4 from the left, my x is slightly less than 4. So if I'm slightly less than 4, say 3.99, then this limit will give me 3.99 minus 3, which is a positive number, 3.99 minus 2, which is a positive number, over 3.99 minus 4, which is a negative number. So total, I will have positive divided by negative, which will be negative, and I know that it's infinity since this is a vertical asymptote. So we had to factor this one first, and then we had to do this, is it positive or negative business. Hopefully that made sense to you. We have one more example. Let f of x equal x squared minus 4x plus 3 over x squared minus 1. We want to determine the following limits and use those to find the vertical asymptotes of f of x. So I want to simplify this function a little bit. I could deal with it as it is, but I want to factor it to make it a little bit prettier. So I'm going to do that down here. I have f of x equals x squared minus 4x plus 3 over x squared minus 1. The top factors as x minus 3 times x minus 1. Again, I want two numbers that multiply to positive 3 and add to negative 4 over x plus 1, x minus 1. Well, check it out. These x minus 1s cancel out, and I'm just left with x minus 3 over x plus 1. So I can rewrite this limit as the limit as x approaches negative 1 of x minus 3 over x plus 1. But maybe before I do this part A, right, we're approaching negative 1 from the left and the right, maybe I should check out what's happening on either sides to see if they agree. So let's do parts B and C first. So I want the limit as x approaches negative 1 from the left of x minus 3 over x plus 1. So if I approach negative 1 from the left, I'm slightly less than negative 1. So this becomes, if I'm slightly less than negative 1, then negative 1 minus 3 is a negative number. Slightly less than negative 1, so negative 1.001, plus 1 is still negative. So this gives me a negative number. So I have a negative number over a negative number, which gives me positive infinity. If I look at the limit of f of x as x goes to negative 1 from the right, I have the limit as x goes to negative 1 from the right of x minus 3 over x plus 1. And again, we're slightly greater than negative 1. Regardless, our top is going to be negative. Our bottom, if I'm slightly greater than negative 1, I'm like negative 0.99, for example. Negative 0.99 plus 1 is a positive number. So I have negative over positive, which is negative infinity. And that is it for the, oh, no, we're not done yet. We have to go back to new part A. So because these two limits don't agree with each other, I can see that this limit does not exist. So this does not exist because the right-handed limit and the left-handed limit are different. One of them is positive infinity and one of them is negative infinity. So our limit as x goes to 1, negative 1 in general, does not exist. Of course, we can also say that these two DNA do not exist because they're positive and negative infinity, but we can specify whether or not they are positive or negative. So that's why I wrote it out. All right, that is it for today. Hope you learned something, and I will see you on Wednesday. Have a wonderful day.